GERAD vous parle. On a le plaisir d'accueillir Patrick Munroe. Je vais laisser François Soumy présenter Patrick, puis après on va donner la parole à notre intervenant pour son séminaire.
Bon, alors, Patrick travaille avec moi comme postdoc depuis un bon 2 ans et demi. Bon, il va présenter un des projets sur lesquels il a travaillé, puis il travaille encore. Il a fait un doctorat à McGill en mathématiques, des vraies mathématiques, là, mathématiques fondamentales. Je trouve que c'est une bonne préparation pour faire toutes sortes de choses. C'est comme les gens qui font de l'athlétisme avant de faire du sport professionnel. Bon, ils ne se mettent peut-être pas riches en faisant de l'athlétisme, mais ils se développent de façon très large avant d'aller dans un sport particulier où il y a peut-être plus de marché, disons. Alors, il a fait toutes sortes de choses dans sa vie. Bon, pendant ses études, il y a eu des bourses CRSNG, FQRNT. Il a suivi 15 cours gradués pour s'ouvrir les horizons. Donc, il y en avait des cours obligatoires, mais il y en a pris d'autres. Il a travaillé dans plusieurs entreprises, Bécité, Locopia, associé de recherche à l'UQAM, à l'Université Laval. Il a travaillé en maths fondamentales, il a travaillé en physique nucléaire, il a développé de la simulation. Il a fait pas mal de choses. Et j'ai été surpris en regardant son CV, ça ne m'était pas rendu compte, le nombre de langages informatiques qu'il connaît. Du C, du C++, du Fortran, du Python, du Java, du Prolog. Il s'est développé en .NET. Il a fait du Visual C++. Donc, finalement, c'est quelqu'un qui... bon, il parle 5 langues, peut-être pas de façon très, très... Il ne ferait peut-être pas des articles en allemand, disons, mais au moins capable de les lire. Donc, c'est quelqu'un qui ratisse large et pour faire des projets, disons, en sciences appliquées où on veut faire à la fois de l'application et du fondamental, c'est assez utile de ratisser large pour aller chercher les bons outils pour faire les bonnes choses. Alors, je suis très content de l'avoir avec nous, puis je te laisse la parole.
Merci François pour la belle introduction. Donc, la présentation va être en anglais. Today I'm going to talk about a project that we're doing with Air Canada. And this is a joint work with Paul Zago, Ismail El-Halawi, and François Soumy. So I'm going to talk about the optimization of air cargo shipping plans. So first, I will talk about mention a few facts and figures about the world of air cargo transportations. So in 2018, there were 64 million tons of goods carried by airlines. This corresponds to about $6.7 trillion of goods, which represents itself about 33% of the global trade by value, so almost the third. In the decade from 1995 to 2004, air freight transport has grown about 50% faster than passenger transport. And from 2007 to 2017, it grew at an annual rate of about 2.6%, and it is expected to continue growing like that, more than that until 2037 at a rate of 4.2%. And if you compare with the passenger industry, so it is expected to grow only at a rate of 3.5% until 2037. So here, I think it's important to mention that those numbers, those predictions were done before the pandemic. So right now it's probably a bit, those numbers are probably a bit off, but there are still good reasons to believe that our cargo transportation will grow faster than passenger transportation in the next few years. So a cargo airline it's a company that transports shipment from origin and destination, from origin to destination airports for their clients. And usually they use passenger aircraft. So when it's the case, they store the goods in the belly of the aircraft. So they use the residual capacity of the baggage holds. And they might also use cargo aircraft as well as trucks. And in general, when they use passenger aircraft, they might have, so the number of connections can be bigger than with passengers, because it's not, since it's not, so it depends on the type of shipments, of course, but if it's not like anything perishable or any living animals, then it often doesn't matter that it takes a few more connections or not. whether it takes a few more connections on that. So the type of shipments that that can be transported by plane is almost anything. So we have perishables, pharmaceuticals, living animals, dangerous goods, and some shipments are priority shipments. So they need to be delivered within a certain time, so usually 24 or 48 hours. And there's standard shipments, which in which there is no such limit, and they are not urgent shipments. And clients can be almost anybody as well. So it can be companies, organizations, individuals, like you and me, as well as freight forwarders, which are essentially, they are companies that are intermediaries organizing shipments for a group of clients. And in general, so there are two types of reservations: the single reservations. So those are punctual reservations that are made usually in the last month before the departure. And there's something what is called allotment, which is a long-term contract in which it is specified that the airline sells some capacity, some specific capacity for at a fixed price for a long period of time, which is usually 6 months. Now, cargo is multidimensional, so it has a mass and a volume, and it's continuous. Some shipment may be divisible, and some others are indivisible, so depending on the type of shipments. And so one of the peculiarity of this cargo transportation is the sources of uncertainty. So one of them is the capacity. So the capacity is usually unknown until departure, because as I already mentioned, they use baggage holds of passenger aircraft. So so the capacity will depend on the weight of passengers as well as on the quantity of luggage. So both for the weight and volume. And another point that is problematic is that demand is very hard to forecast. One of the reasons is that clients pay usually for what is transported, but not for what is booked. So the booked and the actual quantity may differ greatly. And also not just a little. It may be sometimes there are even no shows. So this is when the client does not bring at all the goods at the airport. And in this case, usually, unless it's with a special contract, there is no penalty incurred by the client. And so in order to mitigate this variability of the demand, air freight carriers often resort to overbooking, which means that they sell more capacity than is actually available. And when this overbooking is not done correctly, so there are, because it's actually it's very hard to do it correctly, there may be something that is called, there may occur something that is called cargo overflow, which is when the quantity of goods exceeds the plane capacity. And in this case, so the airline has to reroute the freight. But in general, unless it's for a priority shipments, for example, they won't incur also any penalty for rerouting the freight. So there's no penalty on both sides of the game. Now I will describe briefly how the booking process works for single reservations, so not for allotments. So usually it takes place 1 month before departure, and so a client would contact the call center of the airline or go to the website, and they will place an order for some specific quantity of cargo. And usually at this time, at the time of the booking, they determine already the route to be taken by the freight. So which means a series of flights that's going to be taken by the freight, as well as when exactly this is going to happen. So usually, so this is up to 1 month before departure, and it can be also it can be done in the last day before departure as well. So in the few days before departure, clients bring their freight to the airport, and So usually they should take place at least 6 hours before departure, because in the last 6 hours, this is when the buildup happens. So this is when the cargo is loaded on the plane. So what we propose to do in this project is to optimize air cargo shipping plans. So first I will introduce some terminology. So an order, so a shipment will call it often an order, a shipment order, and the shipments at the time of the booking, they are assigned already to some routes, which is, as I already said, a series of flights. And when we take all those order route assignments together, we obtain what is called a shipping plan. And the problem that we're trying to solve is, given a transportation network and an initial shipping plan, how can we obtain an improved shipping plan? Here, by improved, we mean a shipping plan that would reduces the chances of cargo overflow, as well as the overall costs, so including the transportation costs. So as I already mentioned, so here, if you look at the timetable above, you see that there's this booking process that starts 1 month before departure. And what we propose to do is to optimize in the last week, because you need, in order for this optimization to make sense, it's important to have enough cargo in the shipping plan, enough orders in the shipping plan already. So this optimization would take place in the last week. And as I said, also, since orders can be placed up to the last day, so once the initial shipping plan that was formed from that is made of the booked orders is optimized, so we obtain this improved shipping plans, and then there might be new orders that would be added to this improved shipping plans until the departure. And at the time of the booking, so generally the airlines will use, they have different tools at their disposal. So they have forecasting tools to determine the capacity that's going to be available on a specific flight. They have also tools to determine the demand and as well as the overbooking rate. And they have also some routing engine to determine which route is available for a specific demand, because it can be the case that, depending on the type of products, some goods may require some specific facilities. For example, if it's perishable, you would need some, it has to be refrigerated. And so it cannot necessarily travel by any type of aircraft and go to any airport. So this is this routing engine that determines which route is available. And they have also some cost calculator that determine the price, the transportation cost, among others, of taking some routes instead of other routes. And so we will suppose for the optimization of the shipping plan that we also have at our disposal those tools. So before I present some optimization model, I have to say a bit more about the different sources of uncertainty that we have. One concept that will be important for us is the show-up rate. So the show-up rate is the proportion of cargo that is actually brought to the airport on the day of departure. So in other words, it's the real quantity of goods that is transported divided by the booked quantity. So for example, if a client places an order of 100 kilogram but brings only 80 kilogram to the airport, then the show-up rate would be 0.8. But it could be also the other way around. It could be that the client would book for only 80 kilogram and would bring 100 kilogram, and then you would have a show-up rate of 1.25 in this case. And a no-show corresponds to a show-up rate of 0. So this is when there is no cargo was brought to the airport on the day of departure. And so it was already known. It's already known since a long time that the show-up rate does not follow a usual parametric distribution. This has been studied in the literature. And so what I mean by the usual parametric distributions are like a normal distribution, exponential, beta, and other parametric distributions like that. And one of the reasons why it doesn't follow such a distribution is the no-show, because it's hard to represent the no-show with such distribution. So here is our histograms that were made from the show up rate of orders that were aggregated over the whole network for a period of a bit less than 2 years. So this comes from real data. And so here it's the show up rate for orders that were placed n days before departures. For example, in the first figure, what we see is the day before departure, the orders that were placed on those days, there's still a non-negligible no-show. And we see what we see is also another kind of distribution that is centered, essentially centered at 1 almost, and that is pretty symmetric, but not completely symmetric. And we have the same thing for the other days, for the first 6 days. So what's interesting to notice here is that the show-up rate increases. So the more days you are before departure, the larger is the no-show rate. And also which corresponds to the first bin, and the bin in the middle, the bin that centered at 1. This corresponds to what happens if those are the clients that bring exactly what they booked, and we see that it's quite high as well. But it decreases with time. So at 6 days, it's much smaller than at 1 day. And so what it means that uncertainty increases with time, which is not surprising at all, which is normal. And if we go further in time and we look at what happens at 1 week, 2 weeks, 3 weeks, and 4 weeks. So we say at 1 week, so it's almost like at 6 days. And then at 3 weeks and 4 weeks, what we still have a no-show rate that is very high. So the first bin that is higher than before. And we have also another distribution, which looks pretty much like a uniform distribution. But what will interest us is so it's, as I already said, we want to optimize in the last week before before the departure. So we will be interested with this kind of distribution here, this kind of histogram. So you see that if you forget about the no-show for a minute and you look at the what remains, it's a distribution that's centered at 1 that looks pretty much like a normal distribution, but thinner and longer than a normal distribution. And it's actually, if you do some normality tests with those data, you will see it's not the normal distribution at all. But we decided to model it saying that it's a combination of of the no-show, which corresponds to a constant random variable taking value 0, and a normal random variable. So we will consider this new random variable, which is a mixture of constant and a normal random variables. So the reason why we use this distribution is, so for the no-show, I think it's clear. For the random variable, so we said it's not exactly a random variable that we have, but there are good reasons to still consider a random variable here. One of them is, just from a mathematical point of view, it makes sense. It's much easier to work with normal distributions than with any other kind of distribution. In particular, you can take additions and you can add them and take linear combinations of them very easily, which is not the case with other distribution. Maybe addition is possible; it's quite easy, but when it comes to linear combinations, it's more complicated. Even if you take something like a gamma distribution or a uniform distribution, it's not that easy to take linear combinations. So just from a mathematical point of view, it's easier, but by itself, it's not a good reason to choose a distribution over another one. And so the second reason is that what will interest us is not the distribution of individual orders, but it's the total quantity of cargo on a flight, because our goal will be to reduce the overflow of flights, and overflow corresponds to the total quantity minus the capacity. So the distribution of the total quantity doesn't have to be as precise as the distribution of individual orders does not have to be doesn't have to be that precise, because when we add them up, we know from the central limit theorem that it should eventually converge to a normal distribution if we suppose that they are independent and identically distributed. Here they are not identically distributed, clearly because some orders corresponding to large shipments that have a large a bigger weight won't have the same distribution as other with smaller weight. But since the capacity of the planes are limited, and we take when we take a sum of all of those orders, this should still resemble to something that may be close to the so the normal approximation may still be a good approximation. And another reason is that some of the orders, as I already mentioned, are from freight forwarders. And freight forwarders, so what they do, they aggregate several orders. So usually there won't be a no-show for freight forwarders, because it's very unlikely that all the several orders that they aggregate have a no-show at the same time. And when they aggregate them, so this aggregation will already resemble to a normal, will look like to a normal distribution, because of in view also of the central limit theorem. So so the freight forwarder is just a special case of this distribution when the no-show is equal to 0. And the last reason is because with this distribution, there are only 3 parameters to be estimated. So the rate of no-show, the mean, and the variance, which is not the case with the histogram distribution, where you would have to estimate some non-parametric distribution, or if you have a distribution with many more parameters, it's harder to estimate. So that's it for the demand. Now for the capacity. The capacity, it's much more simple. So I will go very quickly on that. So capacity is what we have is the residual capacity of the baggage holds. So this means that it depends on the number of passengers as well as their weight, and on the number of baggage pieces and their weight and volume. And it is unlikely that so passenger would weigh much more than another passenger, and same thing for the baggage. There might be differences, but not of an order of magnitude. So when we sum everything together, we end up again with something that looks like a normal distribution. So we can here suppose that we can model this residual capacity as a normal random variable. Now I will introduce some notation. So L will be the set of all the legs. So a leg is a flight, essentially. And D is for demand. So it's the set of all the shipment orders. Omega, the set of the available routes, which is provided by the routing engine. Omega D is the set of all the routes that can be that are available for a specific order, and this again we assume that it's provided to us by this routing engine. And now we can define the shipping plan. So a shipping plan, it's the vector x. So every element is x d omega. So it's equal to 1 if the order d is assigned to route omega, and 0 otherwise. And when you take them all together, so we have order route assignment, which is the shipping plane. And we have then the mass and volume of the orders, which are random variables, which are random vectors. So for the mass and volume, so every element corresponds to the mass and the volume of a single order. And we have also the mass and volume capacities, which are also random variables. And each element is the mass and the volume of a single leg, the mass and volume capacity of a single leg. So we can now introduce we can now define the overflow. So A omega L is it's a constant that is equal to 1 if leg L is in route omega and 0 otherwise. So this tells us if a leg is part of a route or not. And so when we define we will first define the total weight of cargo assigned to a leg L as the sum of all the weights, so of the order, so the MD of the orders that can possibly pass by this leg L if they're assigned to the corresponding root. So we end up with this summation here, and we have a similar definition for the volume, the total volume. And for the overflow is defined as the total weight minus the capacity. So it's the max of, so the total weight minus the capacity if this number is positive. If it's negative, so if the total weight is less than the capacity, then there is no overweight. So it takes the overflow is, there is no overflow, so it takes value 0. So that's why we have this max here. And so as I also mentioned that we don't want to only consider the overflow, but we want also to consider the overall costs. So we have to convert this overflow in terms of some costs. And so in order to do that, we introduce some constants, some factor alpha L, so which is an estimation of the cost that would be the cost by unit of mass in excess on a given leg. And we do the same for the volume. And so the total cost for the total mass cost, this OM, is actually just, so you take the cost of so you take the overflow on each leg, you multiply it by this constant, and you end up with this mass overflow cost, and same thing for the volume. We can also consider transportation costs, which are essentially, so for example, the fuel that is used, the number of connections, if there are some administrative fees in using more connections than other. Also in the case of priority shipments, where there may be some penalties. So this delivery delay penalty is included in those transportation, in those additional costs. And we suppose that this vary linearly with the mass. So which makes sense, because usually the price depends also linearly on the mass. And so the total cost, so we multiply the mass by some gamma d omega, which depends on the order gamma and the root omega. And when we take the sum of this all, we obtain this C of xm, which is a linear function of x d omega and a linear combination of md, of the random variables md. So when you put everything together, what you get is the total cost. And the model is just the minimization of the expectation of this total cost, and subject to two constraints. So it's fairly simple. The first constraint says that every order has to be assigned to a route and to a single route. So this is from the definition of the shipping plan. And the second constraint says that an order cannot be divided. So here we suppose that the orders are indivisible. And in general, we won't want to necessarily to reoptimize, to reassign all the orders. We may want to have a large portion even of the order fixed. For example, those that are priority shipments, we don't want to move them because we may have to pay some penalty in this case. So in this case, when we don't want to reassign an order, we consider it as the variable x d omega as a constant in the model. And we can also add an additional constraint which limits the number of reassignments. So here it's not for a specific order, but it's in general. For example, we don't want to have more than 100 of reassignments or 1,000 of reassignments in the whole network. So we can add this constraint here, which counts the number of reassignments. So the first model that we can, the simpler model that we can have with those with this is when it's in the case where the quantities are deterministics. So if the mv, m bar, and v bar are constants, so then we can just remove this E, so this expectation, and it boils down to just minimizing the sum of the costs. And so here, one of the problem is that there's this max function. So this max function makes this objective function nonlinear, but we can linearize it using some slack variables, which is a standard technique. And so another way to deal with this expectation is to use the sample average approximation. So SAA, so we'll call the resulting model the SAA model. So the idea is to replace this expectation by a simple average. So we generate a sequence of realizations of the random vectors, which we will call scenarios, and you take the sum of you evaluate for each scenario, you evaluate the overflow, and then you take the average. And this, when n is large enough, this should converge to the expectation. So this is the Monte Carlo method, and it's a consequence of the law of large numbers. And same thing for the volume. And finally, for the expectation of the transportation cost, since it's a linear function and the expectation is a linear operator, so it actually what we have is just the expectation of each order, which is known. It's the expectation. It's let's say essentially the expectation of our distribution, but it's easy to compute because it's the expectation of the normal random variable weighted by the no-show factor. So it's a constant easy to evaluate here. And this model has the same problem as with the deterministic model in the sense that there's a max, and then we can linearize it, and we obtain this here. But now, when we linearize this model, and if you look at this, you will see that there are a lot of the number of constraints as well as the number of variables increase very fast when we increase the number of scenarios. So the model so the size of the model increases quickly with the number of scenarios. So that's one of the problems with this approach. And also we need a criterion to determine what is the right number of scenarios. On the other hand, this model has the advantage that we can feed it with any kind of distributions. So not necessarily this mixture distribution of a constant and a random variable, normal random variable. We can use any histogram distribution, for example, with this model. So because the model becomes very large very quickly, so we decided to try to find another approach, which is to actually evaluate the exact expression of this expectation. So here I will explain the idea behind this. And so for the sake of clarity, I will assume that the capacity is deterministic. But this is we could leave this hypothesis. It's not a very restrictive hypothesis, but just for the sake of clarity, I will assume that it's deterministic. So here I will not go very much in detail. But the idea is it's essentially just a calculation. So by definition, so the expectation of the max is what you see in this this integral here, and here the FXL is the probability density of the total of XL, which is the total weight on the plane. So it's a sum of random variables that all have this mixture distribution. If it were only a sum of normal random variables, it would be easy. We would know that a linear combination of normal random variable is also a normal random variable. So we would be able to find the probability density and to compute the integral, but it's not the case. So here, what we do is we would like to reduce the problem to this case. So we look at all the possible configurations of a no-show, which means that, for example, if you have 5 orders on a flight and 2 of them are no-shows, then there remains only 3 of them, and those 3 will follow a normal distribution. So when you take the sum of them, you end up with also a normal distribution. But there are depending on the number. So if DL is all the orders that could potentially be assigned to this flight, so there are 2 to this quantity, 2 to this number subsets to this number possibilities of no-show configurations, which is a large number, but I will explain later how we can deal with this. So the idea is we enumerate all of those possibilities, and we just condition on each possibility, which is what you have here in the expectation. So this is called the law of total expectation, and in the end you have this sum here with an integral, and in this integral it's xl, it's the density of xl given some configuration. So it's a normal random variable in this case. So we just have to compute this to evaluate this integral, which gives this expression here. And if you normalize, so the MIL, so you normalize the weights and the average weight and the standard deviation, you obtain a more compact expression here. So it's a sum of some function e depending on this normalized, the normalized average and the normalized variance, and the function e is this function here. So there's inside there a narrow function and an exponential function. So it's clear it's not linear, but it looks like that. It's convex. And it's a function of two variables. So we have some hope that we can optimize, we can minimize this function, but still we would like to use some linear solver, so we'll have to linearize it. So we tried by linearizing the surface using planes, but it didn't give good results. So we decided to use the fact that actually there's some relationship between variance and average. So if the average weight on a plane is bigger, so the variance will be also bigger. So the variance increase if the average increases. But it's not a simple relationship because it depends on the different configurations, depends on the specific weights of each shipment and on the plane. So what we do is that we assume that we suppose that this variance increases linearly as a function of the standard deviation, and we get this curve here. So which is a mix of, if you look at the curves here, so it looks a bit like so those are curves for different value of the variance, and so it's like if you start at with the curve 0 here, and you end up with the curve at 0.5 here. So you have a curve in between, which looks like that. And this curve is, so we can approximate it using a piecewise linear function, and then we end up with a linear model. So this is for the problem with the nonlinearity of the function e, but there's also this other problem of the fact that the number of subsets of DL, which are the orders that can be assigned to the leg L, increases exponentially with DL. So in order to deal with this problem, the idea is it's just that we not all the orders have the same importance in terms of the expectation of overflow. So the largest orders will certainly have a bigger impact on this expectation, because if a larger order is a no-show, there will be a large part of the the capacity that would be spoiled. So it's important to take them apart. So the idea is to take them apart, to consider them separately, and to take the remaining orders together and to make a normal approximation. So for the let's say, like if you have a flight with 20 orders, so you may take, for example, the 5 largest ones, and you condition on all the possibilities, the 2 to the 5 possibilities, which is only 32 possibilities, and the remaining orders, you put them together and you say that in view of the central limit theorem, it should resemble a normal distribution. So now we carried out computational experiments using those models. First thing that's important to say is that the data that was available to us, that were available to us, are insufficient to evaluate the potential economic benefits of our approach. In particular, because we don't have any information about the cost, and also we don't have enough information about the demand to be able to evaluate the economic benefits. So we we still decided to carry out the preliminary simulation experiments with the aim of comparing the analytic model with the SAA model in terms of computational time and precision. And so this was this was the first objective. And the second objective is to test the robustness of the analytic model, because the analytic model assumes a normal distribution plus the no-show, which is not what happens in reality. As you saw, you saw those histograms, so it's not exactly a normal distribution. So it's important to test whether it will still work with it will still work with other kind of distributions. So for the experiment, we even though we used some simulation, we did some simulation. We actually use a real network, so with the real flights. And we also with the real we used real routes, so we didn't have access to the solver used by the company, but we used routes that were taken in the past. So those are realistic routes. And the demand was simulated, so which is due to the fact that we don't have enough information. And this is probably the weakest point in those experiments. But still, we considered a realistic number of shipments, so that we have problems of the same, essentially of the same size as the real problem. And we also considered a realistic general distributions of weights. So which means here by general, I mean that it's the distribution over the whole network. So not specifically for each OD, because we don't have enough information about that. And also for the distribution of the show-up rate, which is a very important part. So we use a real distribution, so which essentially corresponds to the histograms that I showed you before. And for the cost, so we don't, as I said, we don't have information about cost. So we suppose that there is no cost. We suppose that there is only a mass cost that is uniform and equal to 1. So in the end, what we have is just the overflow over the whole network. And we also suppose that capacity is deterministic. But this is not a big issue, because it doesn't simplify the model that much, saying that the capacity is deterministic, because it just I didn't show it in the proof of the analytic formula, but it boils down to adding just one demand by plane that has no-show. So in terms of complexity of calculations, it should not have any effect. So for each experiment, what we did is that we generated 100 sample weight vectors that were generated from some show-up rate distribution. And we compared the overflow reduction of the different models. So the overflow reduction is defined as follows. So so if you look at what's inside the summation, it's just the overflow that is obtained by the initial shipping plan, which was generated randomly, and minus the overflow obtained from the optimized shipping plan. And you divide this by the initial shipping plan, which gives you the reduction obtained for this sample, for a given sample, and then we average over all the sample. And all the models were solved using with CPLEX using an optimality gap of 2%. So at the beginning, what we have to do before comparing the models among them is to fix some parameters. So for the SAA model, we have to determine the right number of scenarios. So here, what you see is a graph where you have the overflow reduction, which is this full line here, and you have the solution time, which is the dashed line here. So the solution time, with no surprise, increases with the number of scenarios, and the overflow reduction also decreases with the number of scenarios. So here we decided to choose 50 as number of scenarios, which seems to be a good trade-off between solution time and number of scenarios. We did now the same thing for the parameters in the analytic model. So the parameters are first the number of unaggregated demands, so those large demands that we want to take apart and consider separately. So we tried between some numbers between 0 and 7, and it increased. So the solution time increased exponentially with the number of unaggregated demands. So we have to take a relatively small number. Here we decided to choose 4. for the other experiments. And we did the same thing also with the number of linear segments in the linear approximation of the function e. So here we we chose 10. And also this is the first comparative analysis. So here we have, so in green, the deterministic model, in blue, the SAA model, and in orange, the analytic model. So what really matters here is we're not making a comparison of deterministic and stochastic. So it's just a baseline to be able to compare the two other models together. So for example, is one, if let's say that the analytic does not perform as well as the SAA model, it's just to be able to see how worse it performs. So if we have no baseline, it's hard to tell how worse it performs. So this is why I included the green line here, but it's not for the sake of comparison. And as well as those numbers here, they mean nothing because it's not true that we're able to reduce overflow by 12%, that would be able to do that in a real network. And it's not the goal of those, it's not the objective of those experiments. So those numbers here should be just used to compare the models between them, but the absolute value is not important. And so what can be seen here? So also we use here a normal distribution for the SAA and as well as for analytic, because analytic assumes a normal distribution. So for this first experiment, the goal was to see if the approximations that we made with the analytic models are too rough, for example, and that we would get bad results. So if we are not even able to get good results, to get similar results with the normal distribution, we cannot expect to get anything good with another distribution, which is not assumed by the analytic model. So that's why we use here the normal distribution. And what you see on the x-axis is the fixed percentage of the shipping plan. So for example, at 0.4, it means that 40% of the orders were fixed and the other ones could be reassigned. So here on the right, you see the solution times as a function of this percentage of the shipping plan that was fixed. And what's interesting to see is that this solution time is very low until we get to a low percentage of the shipping plan, which is normal, because when the percentage of the fixed percentage of the shipping plan is low, this means that the model is larger. There are more variables, more constraints, and so we have the time increases. And here we see that the SAA models is much slower than the analytic model. In the case when we have a large network, when we have a large number of demands of orders to reassign. We did the same kind of experiments, but now with the number of reassignments. So we let the number of reassignments move from 100 to 2,500, and there's a possible maximum of about 11,000 reassignments. And so the higher this number of reassignment allowed, so the higher the flexibility, and the higher the flexibility is, and that's why the overflow is lower. And at the same time, the more complicated the problem is, the more complicated the model is, and that's why we get an increase in solution time. Which is also here, it's maybe hard to see from the graph, but it's about the 10 times slower with the SAA version. So now for the last experiments, last series of experiments, we looked at we were interested in the robustness of the analytic model. So we tested it with different distributions. So this distribution is what is the information that we have the day before departure. So it looks like one of the histogram that I showed you before. Here there's this no-show that I didn't include, but there's a no-show of 0.159 here. And what we see is that the analytic models performs worse, which is not a surprise, but not that worse when you compare with our baseline, which is the deterministic model here. So that's what we have with this histogram. Now we tested it with another histogram, which is made of the information that we had 3 days before departure, with a rate of no-show of 0.191. And now you see that the analytic and the SAA performs almost the same. They are very similar. And if you go further in time, so at 5 days before departure, now the analytic model performs a bit better. And at 7 days before departure, it's much better with, or at least it's significantly better with the analytic model. Now you might think that this is wrong. There's probably an error, because here what we did is that we used this distribution for the SA model, so the exact distribution, and it's a distribution from which we generated also the samples. So the SA has more information, whereas the analytic model suppose only normal distributions. So it doesn't have it is not trained, it is not optimized with the right distribution. So it doesn't make sense that it performs better than the SA. So here, one of the reasons, one of the hypotheses why this could be the case is that we use only 50 scenarios here, which is the number required when we determine the parameters, but we determine the parameters with the normal distributions. So what it means that actually probably we would have needed more scenarios with this kind of histogram. So, but the time here, there's no, I didn't include the solution time, but the increase in solution time is comparable in the sense that you would have, this is much faster with analytic than with SA. And if you increase the number of scenarios, it would be even worse. It would be maybe not tractable with the SA if you double the number of scenarios. But there are more tests could be done, more experiments could be carried out to figure this out. So let me conclude by saying that we introduced a new a shop rate for the distribution that is made of the mixture of two distributions, constant distribution and normal distributions. And this distribution of the short rate can be estimated with only 3 parameters. We introduced 2 stochastic models, one scenario-based and an analytic model. And we showed using experiments that the analytic model offers precision similar to the standard scenario-based model, but with significant reduction in computational time. And we showed that as well that it's robust, at least to some extent, to the actual shape of the distribution of the shop rate. And in future work, it would be interesting and also very important to evaluate the potential costs. So by using real demand data and real cost data. Also, we could take into account the correlation between the orders. So here we suppose that everything is independent, but it's not necessarily the case. Probably not the case, actually. And we also suppose that the orders are indivisible, but it could be interesting to lift this hypothesis here. So thank you.
Merci beaucoup, Patrick. Donc, on va pouvoir prendre des questions maintenant. We have time for questions.
Si les questions ne viennent pas très vite, pendant que vous allez y réfléchir, je peux faire une remarque. Une des contributions importantes de ce travail-là, c'est avant de développer des modèles d'estimation de demande qui auraient été très détaillés, très compliqués pour estimer les distributions, ce papier-là vient évaluer qu'est-ce qu'il suffit d'estimer. Il suffit d'estimer les no-show rates, les moyennes et les variances. Il n'est pas utile d'estimer plus que ça. Donc, on réduit le travail d'estimation de façon très importante. Et ça permettra probablement d'entrer d'autres considérations, comme par exemple estimer les corrélations, ce qui aurait peut-être pas été, qui a été impensable si on voulait parler de corrélation entre distributions qui ne sont pas normales, qui ont des formes compliquées. On s'embarquait dans quelque chose qui était on n'aurait jamais eu assez de données pour le faire. Donc là, on montre que ce qui est important d'estimer est assez réduit et qu'il sera possible de le faire.
Oui, exactement, oui.
Donc, cette idée-là peut être utilisée à beaucoup d'endroits, dans le sens que déterminer ce qu'on n'a pas besoin de faire, c'est important avant de le faire.
Oui. Mais aussi, juste pour ajouter à ça, j'ai mentionné aussi que on a seulement 3 paramètres à estimer, mais estimer un histogramme, ce que je pourrais peut-être mentionner ici, or I'm going to say it in English, is that here, even if we have if we have so there's a difference between the analytic and the SA model, but actually we suppose that we had the right distribution for the SA model, which in practice is probably not going to be the case. So in practice, it's hard to do this kind to estimate the demand. So we don't know exactly if we had if we trained the model. So if we use this as scenarios, this distribution, but actually if in reality the real distribution is different, maybe the analytic model would have performed better. So here it's there is some the SA model has an advantage that should not maybe have in reality in the real life.
Merci François pour la remarque. Est-ce qu'on a des... Et pour la réponse, le commentaire, Patrick?
I have one question.
Yes.
Very interesting talk, Patrick. Very interesting subject. I was wondering, perhaps I misunderstood something, but what will happen if we just consider the no-show and the show rate, so as a discrete distribution with two different events? What will change in the results? Did you try to do so drop completely the normal approximation?
Okay, if I understood correctly, and maybe I don't, you said that here instead of having a normal distribution, we replace it with only another constant.
Yeah, just a constant, because it seemed to be that you use a variance very reduced, so probably an oversimplification could be perhaps just as good.
Mm-hmm. Yeah, I tried it actually to replace this normal with only another constant here. So to say that this boils down to saying that there's either a no-show or not. But in this case, the problem is that it doesn't take in consideration what happens here. Actually, even if you would have the results are not as good, because there's even though it seems to be small. What we have after the one here, what's bigger than one in the show-up rate, it still have an important impact on the total overflow. So you lose some precision here. You would not get that good results. And the normal is actually not what makes it difficult here in the problem. So introducing a normal is not really much more complicated than having a constant, because you can take the sum, you can take linear combinations of normals almost as easily as constants. So it's not the problem here is really, as you saw when I explained this. This number, the aggregated data, is that this number, the 2 to the n that we have, it becomes large very quickly, and replacing the normal with a constant would not solve this problem. So we would still have this problem. But it's so it's an idea that we tried, that I thought also myself that might be simpler, but actually when we did it, it was not really much simpler.
One thing that we want to study in a future work, it is a distribution where there is a probability to be 0, there is a probability to have a given value, and a normal distribution for the remaining case.
Okay, very interesting.
Some order where we know exactly what will happen with a certain probability, some probability to have nothing, and normal distribution for the noise.
Yeah, exactly. So here at this, thank you, François, for this comment. So here, instead of, since if you look at those histograms here, you see that at 1, it's much higher than what you would get with a normal distribution. So it might be interesting also to include some constant here, include some add to the mixture another atom, another constant degenerate distribution here, and to add over it some normal or something like that, to combine this with a normal, so that we get something more even more precise.
Okay, so I had another question, perhaps, maybe in the same vein as what François was saying. So when you do something, I don't remember the name, but with the non-aggregated demand, do you discriminate between, like you have those big clients, and do you discriminate between the big clients that have multiple other clients and that aggregates them all together and the ones that don't?
It's not exactly that. Here you use the word big clients. I use the word big orders, so big shipments. So it's not here. It's not. It is not. Is it on this slide what you're saying? Because it's not. I'm not talking about freight forwarders here. Freight forwarders is I talked about that before. So freight forwarders usually they don't have. There won't be no show in this case. So for freight forwarders, it's simple. You had a normal random variable in the picture. But here what we have the other is that this number, the number of all the available configurations is very large. It increases exponentially. It's 2 to the number of demands. So if there are 100 demands, 100 orders on the flight, 100 shipments, then this number 2 to the 100 it's impossible to have this number of terms in the objective function. So what we do is that we consider only the biggest one, so the one with the largest weight or the largest volume, and because we think that those ones should be considered separately because they are big and they will have the no-show will have a big influence. Probably a bigger influence than a small order. If the order is for 500 kilogram, it has, there's a no-show, it's much more important than if it's only a 10 kilogram, for example.
Yeah. Okay, and you exclude freight forwarders from those, right?
Yeah, exactly. I mean, exclude. We can include them, but they will with the no-show here. I didn't mention it, but the P that you have here, it's the property of showing up. I did. As if it were the same for every order, but actually we can take a different P for every single order. It's not more complicated. Here it's just you would have. I mean, the expression, the notation will be a bit more complicated, but from the point of view of the model, it's doable. You just instead of having P to the something, you would have a P D1 times P D2 times P D3, etc. So you can have and in the case of no-show, you would in the case of a freight forwarder, you have this P equal to 1.
Okay, so in a real application, for instance, you could have a different P for each order because you know the history of the client that plays those orders.
Exactly. The history or it might be the OD. It might be that on some market, you know that the show up, the no-show is that much, and on other something different. So it has this flexibility.
Okay, thank you.
Thank you for the question.
Est-ce qu'il y a une autre question?
S'il y a certaines personnes qui veulent poursuivre la discussion, envoyez un courriel, send an email to Patrick, and you will possibility to have a Zoom or something else up to you.
Yes, of course. Yeah.
And if somebody have problem with some similarity with it, it will be interesting to discuss. If you know what to use, some similar idea for not necessarily the same kind of problem, but a problem with some similarity. I think that a study the distribution where you have atom and continuous variable mixed together, it's appear in many cases in practice, and it was not so much studied in the literature.
Très bien, je pense il est 16h02, on va arrêter ici le séminaire. Merci beaucoup Patrick pour ton très intéressante présentation. Merci François.
Merci à vous.